Welcome back to the channel. Today we're diving into one of the most fundamental concepts in electricity, the difference between alternating current and direct current. These two types of electricity power almost everything around us, and understanding how they work is key to grasping modern electrical systems. If you find this stuff fascinating, make sure you subscribe to the channel so you don't miss future deep dives into science and technology. Let's start with the basics. Direct current, or DC, is electricity that flows in one direction only. Imagine water flowing down a river in a single direction, from a mountain to the ocean. That's essentially what direct current does. Electrons move from the negative terminal of a power source through a circuit to the positive terminal, and they keep moving that same way continuously. This unidirectional flow is what makes DC so predictable and useful for certain applications. Batteries are the classic example of direct current sources. When you put a battery in your flashlight, the chemical reactions inside create a potential difference between the two terminals. That potential difference pushes electrons through your circuit in one constant direction. The electrons flow out of the negative terminal, through your bulb, and back into the positive terminal. This steady one-way flow is why batteries power devices so reliably. Direct current is fantastic for portable electronics and small devices. Your phone, laptop, smartwatch, and wireless headphones all use direct current internally. Even though you might plug them into an outlet that provides alternating current, there's a power adapter that converts that AC to DC, so the device can actually operate. The DC power ensures that sensitive electronic components receive stable, predictable power. Now let's talk about alternating current, or AC. This is where things get interesting. Instead of flowing in one direction, alternating current reverses direction periodically. The electrons flow back and forth, oscillating between positive and negative. If you picture that river again, imagine the water suddenly reversing course, flowing backward upstream, then forward again, then backward again, constantly switching directions. The number of times alternating current completes this back and forth cycle per second is called its frequency, measured in hertz. In North America, household electricity alternates 60 times per second, so we say it's 60 hertz. In Europe and many other places, it's 50 hertz. This constant oscillation might sound inefficient, but it's actually incredibly useful. Alternating current was developed by inventors like Nikola Tesla and George Westinghouse in the late 1800s, and it became the standard for power distribution across the globe. Why? Because AC has some remarkable advantages, especially when it comes to transmitting electricity over long distances. When you need to send power from a power plant to cities miles and miles away, alternating current wins. The key advantage of AC is transformers. These devices can change the voltage of alternating current without losing much energy. A transformer uses electromagnetic induction, a principle where a changing magnetic field induces an electrical current in a nearby coil. Since alternating current constantly changes direction, it creates a constantly changing magnetic field, which makes transformers possible. Power plants generate electricity at a moderate voltage, but they can't send it all the way across the country at that voltage because too much energy would be lost as heat in the transmission lines. Instead, transformers step up the voltage to extremely high levels, sometimes hundreds of thousands of volts. This high voltage means the current flowing through the wires is much lower, and lower currents lose far less energy to heat. The power travels efficiently across the grid. When that high-voltage electricity reaches your city, substations use transformers again to step the voltage back down to safer, more usable levels. Eventually, it reaches your home at around 120 to 240 volts, depending on your country. This stepping up and stepping down would be nearly impossible with direct current, which is one reason why AC became the standard for the power grid. But here's where it gets even more interesting. While your home receives alternating current from the grid, most of the devices inside your home actually use direct current. That's why nearly every electronic device comes with a power adapter. The adapter contains a transformer to step down the voltage, rectifier circuits to convert AC to DC, and filtering to smooth out the resulting current. Your refrigerator, your television, your computer, your lights, they all have internal circuits that convert AC to DC. LED lights are a great example. The LED bulb itself requires direct current to operate, but it's powered by alternating current from your wall socket. Inside the bulb is a small circuit that converts AC to DC and delivers the right current to the LED. As technology advances and our electronics become more sophisticated, the conversion from AC to DC happens earlier and earlier in the chain. So let's compare these two types of electricity directly. Direct current flows in one direction, is stable and constant, and is perfect for powering individual electronic devices. It's also safer at low voltages, which is why it's used in situations where safety is paramount. Alternating current oscillates back and forth, which makes it ideal for transmission over long distances and for powering large industrial equipment. The efficiency difference is significant. If you tried to transmit DC power across the country the way we transmit AC power, you'd lose enormous amounts of energy to heat in the wires. The voltage stepping that transformers enable is essential to making long-distance power distribution practical. Without that capability, you'd need massive, expensive copper wires to minimize losses, and it still wouldn't work as well. Modern electrical grids are built around alternating current for this reason. It's the reason Thomas Edison's direct current vision for the power grid lost out to Nikola Tesla's alternating current system in the late 1800s. AC simply scales better for the massive infrastructure needed to power entire nations. But direct current isn't going away. In fact, it's making a comeback in some surprising ways. Data centers run on direct current. Renewable energy sources like solar panels naturally produce direct current. Electric vehicles use direct current batteries. As the world transitions to renewable energy and becomes more focused on efficiency, DC systems are becoming more attractive, especially for local power distribution. Some cities and universities are experimenting with DC microgrids. These are smaller, localized power systems that distribute direct current instead of alternating current. Since solar panels produce DC and batteries store energy as DC, using DC throughout the system eliminates conversion steps and wastes. The energy efficiency gains can be significant over the long term. However, it's important to understand that the future probably isn't purely DC or purely AC. Most likely we'll see a hybrid approach where AC continues to power long-distance transmission while DC becomes more prevalent in local distribution and within buildings. This combines the strengths of both systems. Another fascinating aspect is the behavior of these currents in different materials. Direct current flows smoothly through a conductor, always using the same path. Alternating current, though, behaves differently. At high frequencies, alternating current tends to flow near the surface of a conductor rather than throughout its entire cross-section. This phenomenon is called the skin effect, and it becomes more pronounced at higher frequencies. The skin effect is why high-frequency AC transmission requires different considerations than DC transmission or low-frequency AC. Radio waves and wireless power transmission use very high-frequency alternating currents, and understanding the skin effect is crucial for designing antennas and transmission systems that work efficiently. Physically, direct current is simpler to understand and work with. It's predictable, straightforward, and requires minimal filtering. Alternating current, by comparison, is more complex, but more versatile. The mathematics behind AC circuits involves trigonometry and calculus, concepts that don't really apply to simple DC circuits. One more important difference involves safety. Direct current at low voltages is generally safer than alternating current at the same voltage. This is because AC can cause muscle contractions and fibrillation at lower currents than DC. That's why touch-sensitive switches and circuits that might come into contact with your body are typically DC-based. However, it's important to note that both AC and DC can be extremely dangerous at high voltages, so respect for electricity is always warranted. Let's also consider power calculation. With direct current, power is simple. It's just voltage times current. With alternating current, Because the voltage and current are constantly changing, you need to account for something called the power factor. The power factor depends on the phase relationship between voltage and current, which is determined by the types of loads in the circuit. Inductive loads like motors and transformers can cause AC current to lag behind AC voltage. This phase difference means the actual power delivered to the load is less than the product of the voltage and current readings. It's a subtlety that doesn't exist with direct current, making DC systems simpler in some respects. In the context of home energy use, understanding AC and DC can actually help you be more efficient. Many of the losses in your electrical system come from converting AC to DC in each device. If you had a home with a DC power system, you could run many devices directly without that conversion loss. Solar systems increasingly work this way, using DC internally and only converting to AC when necessary. Electric vehicles are interesting because they store energy as DC in a battery, then convert it to AC power for the motor. Actually, modern EV motors use AC induction motors, which is why the conversion is necessary. But engineers are working on ways to minimize these conversions to improve overall efficiency. The bottom line is that alternating current and direct current are both essential to our modern world. AC powers long-distance transmission and major infrastructure. DC powers our portable electronics and increasingly our renewable energy systems. Understanding the strengths and weaknesses of each helps us appreciate how our electrical systems work and where future improvements might come from. As technology continues to evolve, the interplay between AC and DC becomes more nuanced. Smart grids will need to balance the transmission efficiency of AC with the local efficiency of DC. Electric vehicles will continue pushing development in DC systems. Renewable energy will keep DC relevant. The conversation between Edison and Tesla, in a sense, never really ended. I hope this explanation has clarified the difference between alternating current and direct current. These concepts are fundamental to electrical engineering, and understanding them opens the door to a deeper appreciation of how modern technology works. If you found this video valuable and learned something new about electricity, please give it a like. It really helps the channel grow and lets me know what topics you find most interesting. Now I'd love to hear from you. In the comments section below, tell me which type of current do you use most in your daily life? Or if you could design a power system from scratch, would you choose AC, DC, or a combination of both? I read every comment, and I'm always curious about your perspectives. Thanks so much for watching, and please subscribe to the channel if you haven't already, so you get notified when we explore more topics in science, technology, and engineering.